Now we'll take a look at Seneca Rocks from Google Earth. Type that into the search bar here. Google Earth should take us there. There we go. Alright, we'll let it zoom in all the way at first. So in the second video in this series, I was standing in this parking lot, looking off to the east or slightly to the northeast at that big fin of Silurian sandstone that is the topographic feature Seneca Rocks. Google Earth takes you to a little sort of crossroads settlement here. We'll go ahead and clear that out so we can see everything a little more clearly. Of course, the value of Google Earth is to be able to incline this view and then zoom out just a bit further so you can fully appreciate the structural context of that very dramatic outcrop of sandstone that is such a very interesting topographic feature to see when you're standing down here on the headwaters of the Potomac River looking up at it. So the steep beds there are in the vertical to even slightly overturned in some places, and we'll see that in just a moment. Forelimb of the anticline. This is the less steeply dipping back limb that makes that higher ridge that sort of looms over Seneca Rocks from the background. And collectively, these topographic highs frame this axial valley that is developed on top of Ordovician carbonate rocks that are very susceptible to chemical weathering in the Appalachian climate. They tend to produce topographic lows and almost always karst features as well, and that's certainly the case here. There's lots of caves and caverns within this axial valley. What's very interesting to do here is if we move just to the northeast along strike, we can follow these forelimb beds, and here we see that they actually sort of wrap around into a nose, and there's some sort of a transfer zone type of structure here where this specific anticline takes a slight jog, there's a slight shift in structural style, and ultimately what you see slightly to the north of this nose is just a little bit structurally different than specifically what you see in this feature that we call the Wills Mountain anticline. And if we zoom back in just a little bit, you can see here you can actually follow those resistant Silurian sandstones right around through that nose and over into the back limb, which continues along the higher ridge and then produces that much taller topographic feature that is not nearly so steep or dramatic, but because of its lower dip, it's certainly capable of supporting higher elevations. And if we follow this vertical forelimb down along strike, you can see more vertical bedding, and if you were to continue along the entire length of this feature, you would occasionally see slight shifts in dip. Here the beds are still very steeply dipping, but they're dipping ever so slightly to the northwest. But ultimately, the structural style that we've seen is consistent for many kilometers along strike. So we'll go back to Seneca Rocks up here, and you can follow this again for, I actually don't know how far, probably 10 or more kilometers. And certainly well over 10 kilometers if you follow this anticlinal structure along its entire length. Now, the third video from the overlook was filmed right in this area here. Here we're looking at the summit of Spruce Knob, highest peak in West Virginia. This is a very broad syncline that has only a tiny erosional remnant left. This is Pennsylvania Nage rock. It's a sandstone or pebble conglomerate. It's very resistant to erosion, and it's having sort of a capping function that is still supporting this very elevated topography adjacent to these very steeply dipping beds at the structural front. And when I was standing at the overlook, I would have been somewhere in this area. I don't know precisely where, but I was looking out across the valley at these vertical beds on that vertical to even slightly overturned forelimb, and these are really exactly the same thing that you're looking at Seneca Rocks. The topographic expression isn't quite as dramatic, but you can certainly appreciate those similarities. Very steeply dipping to vertical Silurian age sandstone, and here we rotate our perspective ever so slightly. The imagery and the reproduction on the elevation model is good enough that you can really appreciate how those ribs or sort of fins again stick up above the surrounding topography above these less resistant lower Devonian and upper Ordovician strata. Now, the fact that you can today stand at high elevation in a synclinal structure, preserving these younger rocks further out in the foreland, tells you that there's been a lot of erosion going on here. For these materials to be deformed into this syncline that is now structurally sort of disconnected, if you will, from the rest of the ridge by erosion, you would have to fill all of these valleys back in with rock at least to restore the wedge geometry to allow the compressional stress that produced these anticlines to be further transmitted out into the foreland and continue producing deformation for many tens of kilometers to the west. So even though this is referred to as the Appalachian structural front or the Allegheny structural front, it certainly isn't the foreland limit of deformation. And to communicate those stresses, we'd have to restore this as a wedge. You've seen that sort of wedge geometry in the models, including the model that's used as an example in the first video in this series. And to fill all this rock back in at least even with the top of this syncline, you'd have to put back about 800 meters, approaching a kilometer in some places. And this Pennsylvanian rock is certainly not the top of the section that would have been present in the Appalachian Foreland Basin. So you're looking at the results here of probably, well, at least a kilometer and change of erosion, and probably 2 kilometers or maybe even more. I've never actually seen anyone attempt to fully restore the Alleghenian or Appalachian fold thrust belt to its assembled but uneroded geometry. Of course, that would be extremely challenging to do given the depth of erosion, but the simple fact that this syncline exists and the outcrop of the structural front is now below that is very good evidence of very extensive post-assembly, post-fold thrust development erosion, and certainly that type of evolution is what makes this entire landscape look like it does today. This is a fold thrust belt that was once much thicker. It's lost, again, probably kilometers of material to erosion, and resistant rocks have been etched out so they stand out in topographic relief. So taking an overall view, here again we see the back limb of the Wills Mountain anticline. You have to imagine it arching over and coming down into its vertical forelimb here. There would be one or several thrusts or splays of thrusts in outcrop in this valley. They're probably buried underneath alluvium, modern alluvium in this river valley. If we could scour all that away, we'd be able to see those thrust structures. And if you actually look at the grain of the topography, you can see that those very steep dips continue across the valley until you reach these flatiron type of features. Here, the strata are dipping off to the northwest. That dip decreases to the top of the plateau here where the layers are almost flat-lying, but then they dip back down to the northwest yet again. And if we zoom in on this valley, we can see more flatirons suggesting that northwest dip. So collectively, this big plateau area is sort of an undulating set of folds. They tend to be much more broad and open than the structural style you see in the rest of the fold thrust belt back to the east, and that's why this area supports such high topography. In an erosional setting like the Appalachians, where lithology controls topography, low dip is good for supporting elevation, particularly when that involves very resistant beds. So these broad and more open folds involving these very resistant sandstones are just tailor-made to support these high plateaux that stand up above what is a structural feature, I guess, that is associated with more extreme compression and certainly an ever so slightly thicker part of the wedge, at least prior to the erosion that's made this landscape look like it does today. Now, one thing I told you in the third video that I was a little bit off on was that the top of this ridge is a regional drainage divide. I was about 1.5 kilometers off. The top of this ridge is the regional drainage divide, but certainly this easternmost edge of the plateau is the regional drainage divide to the north of Spruce Knob, and then again to the south as well. So if you're standing in this area, this is called the Dolly Sods. It's a very interesting place to visit in eastern West Virginia. You can stand right up at the edge of the plateau here and look off into a river valley that drains out to the east to the Atlantic Ocean. Behind you is an elevated and sort of almost swampy or boggy landscape that drains to the Ohio River and then to the Mississippi and into the Gulf of Mexico. So certainly that plateau edge, the edge of this broad synclinal structure, is a regional drainage divide again to the north and the south of Spruce Knob, but specifically at Spruce Knob, where I was filming that third video, the drainage divide has already stepped one more ridge over to the northwest as these Atlantic streams have sort of continued to eat their way into this big structural mass. But certainly that drainage divide is associated with the outcrop of these much more open and broad folds that are great topography formers here in the Appalachians. Okay, so take a look at this on Google Earth if you get a chance. In some respects, I think it's almost a better way to see and appreciate these structures because it'll let you see the entire regional context. Of course, if you're standing down the valley just looking up at Seneca Rocks, it's very impressive. But from this vantage point, we can actually see this big breached anticline. You can see the nose of the anticline like we looked at the start of this video. And ultimately you can put these features into an overall structural and erosional context and essentially explain to yourself, I guess, why they look like they do. And certainly the exercise that we've applied here can be applied to any of the other features that you see really anywhere else here in the Appalachian Fold Thrust Belt, particularly in the mid-Atlantic region and further south where these features were not glaciated. In glaciated areas, the lithologic control is certainly still there, but you start to see a little more complexity that's the result of ice altering the landscape appearance and drainage patterns. But most certainly in this region and further south, you can do a great deal of very interesting structural interpretation simply by looking at features from the Google Earth vantage point. So hope you enjoyed these videos. Check them out here and hopefully we'll have more to come.